This call is now being recorded.
Dear students, we'll continue the unit number 3 on voltage regulators. I hope you can see the screen. Last time we had discussed about the discrete voltage regulators. In that we have seen a Zener voltage regulator, transistorized voltage regulator in brief, and then we have seen IC regulators, in which we have seen fixed IC voltage regulators like 78XX, which is used for positive output voltage regulation, then 79XX for fixed negative output voltage regulation. Then we have seen variable IC voltage regulators like LM317, which is used for variation of output from 1.25 volts to 37 volts positive. And also we know that LM337 is for negative voltage variation, which varies from minus 1.25 volts to minus 37 volts. So as with this background, we will go further and we will see what is dual power supply in this case. As we know that all this dual power supply, regulated power supply, what we are studying till date are all linear voltage regulators. In that we have seen single power supply voltage regulators. Now today we will discuss over here in this point as what is dual power supply. So dual power supply, we have positive voltage as well as negative voltage both in the circuit diagram as shown over here on the screen. And this particular has many applications, and it can be used in operational amplifier where we need positive VCC as well as negative VCC. As we know in op-amp, we require plus 15 volts, minus 15 volts as dual power supply. So this is a very best application of dual power supply in operational amplifiers. So you can see the first diagram on the screen where we have a transformer step down, where you can see 230 volts step down to 15 volts. Then we have 4 diodes which have been used in bridge rectifier, full wave rectifier circuit. Then we have capacitance as filter over here to reduce the ripple. And then we have 2 Zeners, you can see over here, 12 volt 1 watt Zener diode. And then again we have another 12 volt 1 watt Zener diode used over there. So with reference to 0 volt, we have plus 12 volts and minus 12 volts. So we can get 2 voltages at the output where it is fixed again. So we have plus 12 volts fixed voltage and minus 12 volt fixed voltage. Similarly, you can see another diagram over here as dual adjustable power supply, where we are going to use LM317 for positive variation in the output voltage, and we have LM337 which is used for negative voltage variation in this case. So again we have a center type transformer over here, you can see. Then we have a bridge full wave rectifier with 4 diodes. Then we have capacitance filter over here. Then we have LM317 and we have LM337, and then we are going to get the output with respect to ground as plus 1.25 volts to 37 volts on the positive side, and we are going to get minus 1.25 volts to minus 37 volts on the negative side. So this is a complete dual power supply design aspect using a Zener on the above circuit, and we have IC, variable IC on the below on the screen. So I hope you are having a very clarity about what is dual power supply. Now when we talk about LM317, we have output current 1.5 amperes, output adjustable voltage from 1.2 volts to 37 volts. Then we have internal thermal overload protection, internal short circuit protection. We have output transistor safe and floating operation for high voltage applications. And we know that LM317, this particular IC is in transistor package used. So we have another point over here to discuss over here is the current boosting circuit using voltage regulator. Now see friends, when we are talking about 78XX over here, you can see on the screen, This particular IC, for example, have the specification. By using the data sheet, you can understand that output current of this IC is, for example, 1 ampere. So if I want to go and draw more current from this IC, then I need to change the IC, and we have to get the IC with specification greater than 1 ampere. But how to achieve the current more than 1 ampere? That circuit is called as current boosting circuit using voltage regulator. So in this particular circuit, you can see a transistor Q1 connected in parallel with the IC, and thus there will be a sharing of current, collector current, and the output current of this IC, and the total output current at the load we can get, which will be the addition of collector current and the output current of the IC. So then that means that if we want to increase the current limit beyond the specifications of the IC78XX, that can be achieved using a transistor Q1 as shown in the figure on the screen, and thus we can increase the output current limit of a regulated IC78XX. So this is a very important circuit which was implemented in our college at that time, because now I think we do not have this particular circuit to be implemented in our syllabus. But I was very fortunate to have good colleagues with me, like Dr. Sandeep Mushe sir. Then we have Professor Mahesh Poddar sir, and we used to all together implement this particular circuit in our college, and we had implemented over here. The most important thing is that design of this particular circuit was also a crucial part. And as you know that if I want to go beyond 1 ampere current at the output, I need the input transformer has to be beyond 1 ampere current rating of that particular transformer. So this was a great experience what we had at that time. So in 2009 2012 course, we had this particular experiment in our syllabus, and at that time we had implemented it in our college. This was the uh, values, and this were the circuit diagram which was been implemented as what I was discussing. So we had used for 7805 IC, and as I said that it has 1 ampere output current, and we had drawn approximately 1.5 current at the load with 5 volts at the output. So now next topic of this particular unit we are going to discuss over here is the low dropout voltage. So as we know that we have input always greater than the output voltage in linear power supply, of course, and there is a drop between the input and output, and that drop is to be minimized. In order to minimize that drop, we have separate ICs which are called as LDOs, and that particular difference between the input and output is having minimum drop in that case, so that we have relatively best power management solution what we can get over there. So that difference between the input and output for LDOs is approximately 1 volt or 1.8 volts, as you can see on the screen. So we have a 3-terminal LDOs available in the market, and we have again input slightly greater than output, and as we are having the difference, we drop out less, so the dissipation is less, and the efficiency of that IC will be more, and the percentage regulation also can be improved. So we have one particular output equation over here which can be used as R2 plus R1 into bracket divided by R2 into V reference, can be calculated to calculate or to measure the output voltage. So what are the key features, parameters of LDOs? That dropout voltage is to be understood. We have to know what is load regulation, what is line regulation, then what is PSRR, that is power supply rejection ratio. Output voltage is to be controlled by the resistive negative feedback network, and of course input voltage must be greater than output voltage. So these LDOs again come in the same category of linear voltage regulators, because input is slightly greater than the output, of course. Now we have different components used in these LDOs. as what we have seen in normal voltage regulator ICs. We have voltage reference as shown in the figure over here on the screen. We have pass element, that is control element, as transistor, as MOSFET. Some active element over there can be used, across which we have LDOs, voltage drop across the input and output as shown in the figure over there. Then we have error amplifiers using op amp, and then we have feedback resistance, which is having as shown in the figure over there on the screen. So the output current is controlled by the transistor used over there in the pass element, and then we can control it by the error amplifier using op amp. The V reference, which provides constant output voltage, which will be compared with the output voltage from the feedback network as shown in the figure. So we have V reference as a reference voltage, fixed voltage. Then we have the pass element, that is a control element using BJT, in which we can see over here on the diagram that we are going to have some Darlington pairs used over there. Also, we can use MOSFET. So we have PMOS, NMOS, MOS transistors used over there as a control element, pass element. And the output current is controlled by the error amplifier output. Now we have error amplifier using op amp, as we are discussing over here, with the output taken from the resistive network, and it is been compared with the V reference, which is at the positive terminal of the op amp, and the feedback voltage is being given to the negative terminal of the op amp as shown in the figure over there. So with comparison with the V reference and the feedback voltage from the output, we have two cases over here. You can see the case number one, when the feedback voltage is less than V reference, then the gate of PMOS is pulled lower and we can see that the output is increased. And in the second case, if V feedback, that is feedback voltage, is greater than V reference, then the output will be decreasing. So our purpose is that to maintain output voltage constant, but it depends on what is the feedback voltage, and in comparison with the V reference, the output will be increased or decreased. Ultimately, we want output to be maintained constant over here in voltage regulator circuits. We're getting this point. So we have the selection criteria for selecting LDOs. Like when we talk about LDOs, we should understand what are the selection criteria, like input voltage range, output voltage, whether it is fixed or whether it is variable, output accuracy over line or load, and temperature, low current requirements, dropout voltage, PSRR, output noise, quiescent current, and shutdown current. So see, when we are selecting voltage regulator IC, that is LDOs over here, we have to understand what are the selection criteria, and we have to understand all these particular criteria with respect to input range, output voltage, load regulation, line regulation, stability, power supply rejection ratio, and so on. So all these important criteria are being considered when we design and when we have to select an LDO in the circuitry. These LDOs are the best application in mobile phones. As we know that in mobile today, the battery constraint is very important, and everyone wants to know that their battery is lasting more and more. Means if I get a mobile which the battery lasts for 8 days, that will be the best mobile what I can have. But it doesn't happen. These days, we know our mobile battery lasts for 1 day, not more than 1 day. Maximum, we can say some 7 to 8 hours, not more than that. So this is the limitation. Hence, LDOs are used over here in mobile phones. Then we have different applications like PCMCI card. We have cellular phones, we have cameras, we have modems, we have MP3 CD players, and so on. So everywhere today we have gone for LDOs being used so as to improve the efficiency, the regulation, as well as the power dissipation across the control element can also be an important parameter over here. Now, this all, whatever we have seen, was regarding linear power supply. Now we will see about switch mode power supply. So this is switch mode power supply is a different type of power supply which has high power efficiency. Then it has multiple output voltage of different polarities. And what are the different types of SMPS that also we are going to see? Like it is having buck type SMPS, that is step down SMPS. Then we have boost type SMPS, that is step up SMPS. Then we have buck boost, which is also called as inverting SMPS, means the output polarity is inverted with respect to the input. So we will just try to understand why we go for SMPS. So it is again a regulated voltage regulated supply circuit which has efficient transfer of power at the load as compared to linear power supply. Now switching regulator passes the load in pulses, means we are going to have a control element which is being turned on and off, and hence we are saying this as a switching voltage regulators. As we saw that buck means it is going to reduce the output DC voltage as with respect to the input voltage. Then we have boost, means output is higher than the input voltage. Buck boost inverting means that output is having opposite polarity with respect to the input. And lastly, we can say we have flyback SMPS, where we are having less than as well as greater than input voltages, which is also called as multiple outputs in this case. So we have overall 4 types of SMPS which we are going to discuss. This switching voltage regulators is based on the fundamental law of an inductor, where current flowing into an inductor will be time varying even if the forcing voltage is constant. As we know, the voltage across an inductor is given by L di by dt, as you can see the equation on the screen. And as you can see the graph over here on the left hand side, if the current with respect to time is constant, then di by dt is equal to 0, because the derivative of a constant is always 0, hence voltage will be 0 in this case. In the second graph, you can see that if di by dt is greater than 0, then voltage will increase in this case. The third graph you can see on the screen is di by dt is less than 0, then voltage will be less than 0 in this case. So this gives the voltage current relationship in case of an inductor, and based on this particular principle we are going to use it in SMPS for buck boost and flyback type of SMPS. Now let us come to the first type, like buck regulator, where you can see on the screen that we have a switch which is controlled with PWM control. So that switch will be on and off continuously with PWM, and then we have an inductor used over there. And you can see over here that switch is connected before the inductor, and based on the switch on and off, the output will be regulated. And in this buck regulator, we are going to get the output lesser in voltage as compared to the input voltage. The circuit diagram of step down configuration of an SMPS is shown on the screen, and we have step down means output will be lesser than the input voltage, and the control element Q1 is pulsed on and off at variable rate based on the load current, and the pulses are filtered out by an LC filter as shown in the figure on the screen. We have operational amplifier as error amplifier, and the reference voltage is generated across the Zener D2, that is Zener diode as shown in the figure on the screen. Then next one is the boost regulator, where you can see that switch is connected in parallel with the load. If you remember, in buck regulator, the switch was connected in series with the load. In boost regulator, the inductor is connected before the switch, and the switch is connected in parallel with the load as shown in the figure on the screen. And again, when the switch is on and when the switch is off, the inductor will supply voltage in addition with the capacitor voltage, and we will get additional output on the output side, which will be greater than the input voltage over here. So we'll be getting boosting of voltage in this regulator, SMPS. The step-up configuration circuit diagram is as shown in the figure over here, and we can see that the difference is the placement of inductor, and the Q1 is in shunt connected with the output, that is Q1 is connected in parallel with the load. When Q1 is off, then VL is added up to the capacitor voltage, stepping the voltage up, and that's why it is called a step-up configuration of SMPS. So again, we have a operational amplifier used as error amplifier with the reference voltage across Zener diode, that is D2, and we have R1, R2 and R3 as resistive feedback network. As you can see, always the resistance is in series with the Zener. Whenever you see a Zener diode in the circuit, you should see a resistance also in series with it, as R1 is the resistance in series with Zener diode D2. So this is the complete circuit diagram of step-up configuration of SMPS. Then we have buck boost inverting regulator, where you can see on the screen that again the inductor which was connected before the switch, now it is in parallel with the load, and a capacitor as it was in parallel with the load previous circuits also. Only in this case the output will be with opposite polarity with respect to the input. If input is as shown in the figure over here as positive Vin, the output is negative output voltage. So we have opposite polarity getting in case of buck boost SMPS regulated power supply. The complete circuit diagram of voltage inverter configuration is as shown in the diagram over here, and you can see that output voltage is with opposite polarity with respect to the input, and this is achieved by voltage across inductor, forward biasing, reverse bias diode during the off time, producing current and charging the capacitor for voltage producing during the off times. And of course, we know that SMPS having 90% and more efficiency, which can be achieved in the switching voltage regulators. Then last type is flyback, that is single and multiple outputs. So this is one type where you can see that we can get output in terms of positive, negative, plus 5 volts, plus 12 volts, minus 12 volts with respect to ground. So we have different output voltages which can be achieved in SMPS. As also we know that SMPS having more efficiency than linear voltage regulators. Then you can see over here that it is used in high current application with less power dissipation, and voltage regulation in switching regulator is achieved by on and off action, hence limiting the amount of current flow based on the varying line and load condition. As we have seen that the switching regulators has efficiency greater than or approximately 90%, which can be achieved. One thing which is very important, that switching voltage regulators are the costliest voltage regulators as compared to linear voltage regulators. Also, we know that it has efficiency more, so it can be used in different gadgets like laptop, mobile, or in televisions and so on. So for charging of a battery, normal case, SMPS is not preferred. In that case, normal eliminator which we are using to charge our mobiles, which has linear voltage regulators, and it is the cheapest one as compared to SMPS. The comparison between linear power supply and switch mode power supply, this is very important comparison over here. Based on the different parameters on the screen, you can see the dropout voltage is more in linear power supply, and hence which dissipates lot of power across the control element, that is the transistor which is connected as a control element in the circuitry. Whereas in switch mode power supply, The control element, that is transistor, is switched on and off. Hence, it has less dropout voltage. It dissipates less power across that particular control element, that is transistor. Then we can say that input frequency over here is 50 hertz, that is our line frequency. Hence, we have high value capacitor can be used over here. Whereas in SMPS, the input frequency can be in kilohertz or megahertz. Hence, we can use the smaller values of capacitors. The efficiency of a linear power supply is approximately 25% to 50%, whereas in SMPS, the efficiency is much higher, which is approximately 65 to 75%, and more than that also we can achieve up to 90%. Then we have load regulation, approximately same on both the sides. We have line regulation, which is also not much difference over here, you can see on the screen. Then the ripple, which is 5 millivolts in linear power supply, and which we have 50 millivolts in SMPS. The size linear power supply is large, SMPS is comparatively smaller. Weight, then we have EMI very low in linear power supply, we have high in switch mode power supply. The transient response is faster in case of linear power supply, where it is much slower in milliseconds in case of SMPS. Complexity, moderately complex linear power supply, whereas in SMPS, as it is having multiple outputs and various types of SMPS we are having, so it is more complex as compared to linear power supply. So this comparison, if you understand, it gives the more clarity of the voltage regulated power supply, which have been categorized as linear power supply and SMPS, that is switch mode power supply. In summary, what we have studied in this unit is voltage regulator definition. What is the definition? We saw maintaining output voltage DC constant in spite of change in input voltage Vin, in spite of change in load current IL, and in spite of change in temperature. So we are having voltage regulator different types as to maintain output DC constant. Then it is broadly categorized as linear voltage regulators and switching voltage regulators. Then we have two types of linear voltage regulators, like series voltage regulators and shunt voltage regulator. As we have seen briefly, let me tell you what is series voltage regulator, where the control element is in series with the load, and in shunt linear voltage regulator, the control element is in parallel with the load. Then we have seen different types of SMPS, like buck SMPS, we have seen boost SMPS, then buck boost inverting SMPS. There is a mistake over here, that buck means it is step down SMPS, boost means it is step up SMPS, and buck boost means it is inverting SMPS. So students, please, there is a mistake over here, you can see, and the type of SMPS. So it should be it should be a buck means step down and boost means step up. Then we have seen that SMPS are more efficient and it is used for low voltage, higher current applications. Then we have seen IC voltage regulator, like fixed positive voltage regulator 78XX, and we have seen negative output voltage regulator like 79XX. Then we have seen positive output variable voltage regulator like LM317 and negative variable voltage regulator like LM337. Then both linear and switching voltage regulators are available in IC form. One difference what we saw, in linear power supply are used in line frequency 50 Hz, whereas in switching mode power supply are used for higher frequencies in the range of kilohertz to megahertz. Then the current capacity of voltage regulator can be increased in case of linear power supply, which we saw, and it can be increased with the transistor connected in parallel with the IC. And the IC capacity of a transistor, the current capacity of an IC, which can be boosted using a transistor in parallel with the IC voltage regulator. These are the different references what we can use what I have used in my presentation. There is a book, Sonde, by Dr. Sonde sir, which is very nice book on this particular voltage regulator topic. So you can refer that book as well. So I'm very much thankful to you to patiently listening for this particular unit. As I always say that this particular unit is very important because in every gadget we need a power supply, and that power supply should be regulated. And we have to understand what is regulated, what is unregulated, what is IC fixed voltage regulator, what is variable IC regulator. This all comes in linear power supply. And then lastly, we have to understand what is switch mode power supply. That is SMPS. So thanks for listening patiently. Thank you very much. Good day. Bye bye. See you.